All right, let's take a look at lessons 2.3 and 2.4. Today, we're going to be focusing on rewriting exponential functions into equivalent forms, which just means we're going to be transforming exponential expressions. As a reminder, what makes something exponential is when you have some base raised to a power, and that power is where your independent variable would be. So I'll put an x there. That's where your independent power would come. This would be an exponential function. That would be exponential. An exponential function would be any function where you have a base raised to a power, and that power has the variable. We're going to be talking about the different ways you can rewrite those. So some examples today that you're going to see is we will take like something like 5 to the power of x plus 1. And we're going to look and learn how we could rewrite that. In particular, you're going to learn that this could be the same thing as 5 times 5 to the power of x. You're going to see a lot of things like this today. These are equivalent, and that's what we're going to be doing today. It's really applying transformations. Okay, so that's the goal today as we go through. Let me slide that down so you can see better. Is we're going to be looking at a lot of things like that. Before I get going too fast, I want to quickly go through what lesson 2.3 is all the way about, and then we'll spend the rest of the time dealing with lesson 2.4. Okay, so 2.3 is just the basics of exponentials. On this slide here, it goes through the basics. An exponential function has the general form, start there, and I want you to put in a times b to the power of x, where b is your base. Now, in this situation, the initial value is a. Whatever value is right there, that's your initial value. Also, a cannot be equal to 0. And your base needs to be greater than 0. Okay, now this is for exponential functions. A geometric sequence can have a negative base, but exponential functions, the base has to be greater than 0. That's going to be a little bit of a difference. So here are some pictures here. This one is exponential growth. That's when your a is positive and b is greater than 1. You have exponential growth, and they gave you a point there. I'm going to give you more points in a second. There's also exponential decay, and that's when your a is positive and b is between 0 and 1. But those aren't the only two situations. So to show you all 4 possibilities, on the next slide, we're going to fill in a little table. So what we're going to do is we're going to label each one here. If you have a function or an exponential function where a is greater than 0 and b is greater than 1, what you would have is exponential growth. What I want you to do here is we're going to draw and add some points. I want you to put a point here. And let's just draw another point right there that we're going to go through. We're going to label those points differently in a second. But this right here would be growth. I want you to label this as growth. What in the world am I writing? Growth. Let's try that again. There we go. Now, there's going to be 3 key features that I'm going to talk about with every exponential function. The first is they'll always have a horizontal asymptote that they approach. So the horizontal asymptote we're looking at here is this on this side of the graph. It approaches the value y equals 0. So add that in there. This is our first of our key features. This function will approach 0 as it goes to the left, meaning I call the horizontal asymptote right there. That's something, a horizontal asymptote is something you're familiar with from previous classes. But using this class, you could say it this way. You could say there's a limit of this graph. Let's just call it f of x. As x goes to the left, as x decreases towards negative infinity, so it decreases without bound, this graph will approach a certain y value. What y value is it heading towards? 0. Now, it won't be the same on the right. Notice this rises to infinity, and that's why we call it growth. Now, the other 2 key features are this. This initial point here is 0, a, 0, a, put that. to that point. The second point and the third key feature, so first key feature, second key feature, third key feature will be the point 1 comma a dot b. So whatever a and b are, if you multiply them, when you go one value unit to the right, that's where you'd get there. So if a is a 5, b is a 2, 5 times 2 is 10, this point would be 1 comma 10. That's how that works. This point would be 0 comma a. Okay, that's growth. Now let's slide over. This square represents when a is positive and b is between 0 and 1. This is your decay from the previous slide. So the previous slide had both of these. This time, what I'm going to do is I'm going to put my point here and my next point here, and we're going to go through. So this is a decay. Again, it has a horizontal asymptote at 0. So go ahead and approach the x-axis. Add in y equals 0. My asymptote. My key features will stay the same the rest of the way. So what's the formula for the y-intercept? You can look over here. 0a. And the next key feature, the last key feature, this would be, oops, not a first. It's 1 comma a dot b. The last thing I'm going to write is this. If you're saying this graph is approaching this horizontal asymptote, you could write that as a limit. Remember, a limit doesn't tell you where the graph is. A limit tells you where it's going. I'll call this one g of x. This one, as we go to the right, that means as x is increasing without bound, we head to 0. So this is function g this time. This one I named f. Okay, now let's mix it up. What if a is negative? Well, if a is negative, what you have is a vertical reflection. So what I want you to do is on this next graph, instead of it growing up and to the right, it's going to decay down and to the right. This one's going to go down this way. I'm going to have the 2 points be here and there. And I want you this time to draw your graph where it decays. That means it decreases as you go down and to the right. This will also be decay. Now, if you're wondering, wait, what scenario is this? This is when a is negative and b is greater than 1. Go ahead and still put the same key features on. Get used to those. So we'll have that y is, it's approaching y equals 0. These key features should not change. This should be 0 comma a. This point right here will be 1 comma a dot b. Okay, tell me about this limit. What's happening as I go to the left? And I'll call this one h of x. As I go to the left, that means x going to negative infinity. Does my y values increase without bound? Does it, meaning rise without bound? Does it fall without bound? Or is it approaching a flat value? Or is it getting flat? It's getting flat. What's it getting flat with? 0. And so that would be a 0 there. There we go. And last one. Any guesses on how it should look? If I have a negative a and a v between 0 and 1.
Reflection on the x-side.
It'll be a reflection of this graph. So coming up, so if you take your points, just reflect it. So this point will be underneath like that. And so have your graph go up this way. Would you call this growth or decay? I hear growth, and I agree. It's growth. By the way, with exponentials, they're either always increasing or always decreasing. They do not change direction. They're doing one or the other. Add those key values again. So we have 0, comma a and 1, comma ab. All right, this time, let's see, I've named one F, G, H. I'm going to call this one K. This time we'll say the limit of K of X equals as X, this time as it increases without bound. What happens to our value as we get further and further to the right? What happens to our Y's? Does they rise? Do they fall? Or do they get flat? They get flat. They are always slightly increasing, but they're approaching the value 0. Okay, so that really is what lesson 2.3 is all about. It's about understanding how A's and B's work together to give you those graphs. So I have, now that's kind of your notes for lesson 2.3. Now I'll have some just quick hits on one slide. I know it's all small, but then we'll move on to 2.4 material. So here we go. For lesson 2.3, it says here, identify if the exponential function is growth or decay and justify your response. On this one, tell me, what is my, here's what I'm going to do. I'm going to ask for the A value and then the B value. What is my A value on this first problem?
2.
So put A equals 2. Now, if you look back on the cheat sheet, you're supposed to determine if A is greater than 0 or less than 0. Is 2 greater than 0 or less than 0? Okay, now tell me about my base.
1 is less than 0.
Okay, so this time put your base a little bit to the right, not quite centered, and I'll show you why. Our base is equal to 0.6. The option was the base is either greater than 1 or is between 0 and 1. Is 0.6 greater than 1 or in between 0 and 1?
0, 1.
Okay, so that's why I said you scoot it over, because we're going to have less than, or 0 is less than B, which is less than 1. Okay, so find the square that has A being greater than 0 and B being between 0 and 1. Which square was that? Top left, top right, bottom left, bottom right. Which one has A being greater than 0, B being between 0 and 1? Top right, it's this one. So what will we call that?
Decay.
Decay. This is decay. This is the justification right there. Okay, let's see if we can go a little bit quicker this time. On the second one, what's my A?
2.
2, which is greater than 0. What about 7/5? This is greater than 1. Good. So when your A is positive and B is greater than 1, what do we have?
Growth.
Growth. It's growth. Example 3. Just tell me if I need me to slow down. What's my A value? 4/3. Is that bigger than 1 or less? Excuse me, bigger than 0 or less than 0? Greater than 0. What about B? Less than 1, but it's positive, so it's in between 0 and 1. A is positive, B is in between 0 and 1. That would become, once again, picture number 2. And what about the fourth? What can you tell me about the A value?
It's less than 1.
It's less than 1, but that's actually not what matters for A. What matters for A is if it's positive or if it's negative.
Positive.
This is positive, so it's greater than 0. My base is 1.3. What can you tell me about that base? It's greater than 1. So this would be growth. This would be picture 1. All right, examine the function f of x equals 3 times 2 to the x. What are we doing to the initial value 3 when the input is x equals 5? Well, what would happen is this. If you plugged in a 5 there, you'd have 3 times 2 to the 5th. Now, can I multiply the 3 and the 2, the a and the b? Can I multiply those right here? What do you think? Can I multiply right here and say that's the same thing as 6 to the power of x? Is that true? No, that's not a true statement. And here's why. Because if you plug in a 5, this would be 3 times 2, and there'd be times 2, times 2, times 2, times, there's 5 2's. Is that the same thing as the 6 to the x power? No, this is not 6 times 6 times 6 times 6. It's this. So that's what's happening there with exponential. No, you cannot simplify a and b. So that's the note here. Just note a and b do not simplify together. A and b do not simplify together unless a equals b. That's the one exception. If they're equal to one another, then you can simplify them. But other than that, if they're not equal, you cannot simplify them together. All right, the next one, let's just simplify this. We have 4 times 4 times 4 times 1.5. Which value is a? What do you think is a in this scenario? Okay, what made you say 1.5 is the a?
It's not repeating.
Okay, so that would be the a value. It's 1.5. And the repeating value is your base. My base is 4. And put an x here. You know, you might be saying, why am I putting an x when there's 3 of them? Because this is saying to write the equation. So that's where the equation came from, where x equals, and this is where I want you to put the 3. Okay, last one, we'll close it on lesson 2-3. How would we write this one? Which value is a? 3.2. It's the one that's not repeating. What is my base that repeats? 0.8. For your equation's sake, put an x there. But for this particular example, how many x's did I have? 2. So x equals 2.